In statistics, one-way analysis of variance is a technique used to compare means of two or more samples. This technique can be used only for numerical data. The ANOVA tests the null hypothesis that samples in two or more groups are drawn from populations with the same mean values. To do this, two estimates are made of the population variance. These estimates rely on various assumptions. The ANOVA produces an F-statistic, the ratio of the variance calculated among the means to the variance within the samples. If the group means are drawn from populations with the same mean values, the variance between the group means should be lower than the variance of the samples, following the central limit theorem. A higher ratio therefore implies that the samples were drawn from populations with different mean values. Typically, however, the one-way ANOVA is used to test for differences among at least three groups, since the two-group case can be covered by a t-test. When there are only two means to compare, the t-test and the f-test are equivalent. The relation between ANOVA and t is given by phi equals AT2. An extension of one-way ANOVA is two-way analysis of variance that examines the influence of two different categorical independent variables on one dependent variable. Assumptions: the results of a one-way ANOVA can be considered reliable as long as the following assumptions are met. Response variable residuals are normally distributed. Samples are independent. Variances of populations are equal. Responses for a given group are independent and identically distributed normal random variables. ANOVA is a relatively robust procedure with respect to violations of the normality assumption. If data are ordinal, a non-parametric alternative to this test should be used, such as Kruskal-Wallis one-way analysis of variance. The case of fixed effects, fully randomized experiment, unbalanced data, the model. The normal linear model describes treatment groups with probability distributions which are identically bell-shaped curves with different means. Thus fitting the models requires only the means of each treatment group and a variance calculation. Calculations of the means and the variance are performed as part of the hypothesis test. The commonly used normal linear models for a completely randomized experiment are: or, where, is an index over experimental units, is an index over treatment groups, is the number of experimental units in the JTH treatment group, is the total number of experimental units, or observations, is the mean of the observations for the JTH treatment group, is the grand mean of the observations, is the JTH treatment effect, a deviation from the grand mean. Are normally distributed to zero mean random errors. The index I over the experimental units can be interpreted several ways. In some experiments, the same experimental unit is subject to a range of treatments. I may point to a particular unit. In others, each treatment group has a distinct set of experimental units. I may simply be an index into the list. The data and statistical summaries of the data. One form of organizing experimental observations is with groups and columns, comparing model to summaries, and the grand mean and grand variance are computed from the grand sums, not from group means and variances. The hypothesis test: given the summary statistics, the calculations of the hypothesis test are shown in tabular form. While two columns of SS are shown for their explanatory value, only one column is required to display results. Is the estimate of variance corresponding to of the model. Analysis summary: the core ANOVA analysis consists of a series of calculations. The data is collected in tabular form. Then, each treatment group is summarized by the number of experimental units, two sums, a mean and a variance. The treatment group summaries are combined to provide totals for the number of units in the sums. The grand mean and grand variance are computed from the grand sums. The treatment and grand means are used in the model. The 3DFs and SSs are calculated from the summaries. Then the misses are calculated and a ratio determines F. A computer typically determines a p-value from F, which determines whether treatments produce significantly different results. If the result is significant, then the model provisionally has validity. If the experiment is balanced, all of the terms are equal, so the SS equations simplify. In a more complex experiment, Where the experimental units are not homogeneous, row statistics are also used in the analysis. The model includes terms dependent on. Determining the extra terms reduces the number of degrees of freedom available. See also, F-test, references.